Alexander Slata is a Microsoft MVP and a managing consultant at Excella, based out of Washington, D.C. He's an international speaker and has spoken at conferences such as NDC London, NDC Melbourne, ProgNet, Big Data Europe, .NET JetBrains, Global Online Day, and many others. He's co-founder and organizer of the virtual ML.NET Community Conference and the organizer of the .NET PC User Group. In his spare time, he enjoys supporting and building a vibrant developer community and spends his time working on the open source project MLOps.NET. Say hi on Twitter at Alex Slata, or tune into one of his live streams on his Twitch, Twitch TV/Alex Slata. So that all being said, let's welcome Alex for his talk. If you want to share your screen, I will put your video live and then I will pair up your content as you're getting ready.
Sounds good. I think my screen is shared and I moved things away so people can see, so that's awesome. Well, thank you, Stan, for that introduction, and thank you everyone who's joined into this talk. This gray and fairly rainy and fall weather Saturday afternoon here. And in today's talk, I hope you're here for listening to ML.NET and hearing more about machine learning.NET. And I promise you we'll dive really deep into both machine learning today as well as the .NET side of things here. But as Stan already mentioned here, I stream every Saturday on Twitch. So I was supposed to do it this morning, but I did that yesterday evening instead. And what I do on Twitch is I focus primarily on machine learning.NET, and I work on this MLOps.NET tool, which is a open source library to support the kind of DevOps cycle of machine learning in the .NET space. So if you are curious more about that after this talk, definitely check in on the Twitch stream, or you can just kind of join into the community that develops this tool. We're more than welcome to have more contributors or anyone using the tool as well. Just a shout out as well, there is going to be a second edition of the virtual ML.NET conference this fall in early November. We're going to do a hackathon. So if you find this interesting today, definitely tune into that, and we will kind of build machine learning models together in .NET and form groups and teams around that. So it should be really fun. But today you're here to listen to ML.NET. So let's get started.
Commander Riker's team is aboard, sir. Helm, warp 1, engage!
I like to start things off a little bit, especially on a Saturday, with something more fun and more entertaining sometimes than just pure theory. But there we go. So what we're going to talk about the next 45 or 50 minutes or so before we take some questions here. Well, I want to start off by giving you a brief introduction to machine learning and dive a bit more into what deep learning is as well, and contrast those two together so you get a strong foundation on what it's all about. And then I want to tune us into the model lifecycle, because I think it's very often overlooked in machine learning talks or in any kind of education on this topic, is how do we actually build a machine learning model? What are the steps, and what is whole churn? What is that going through? Because they're very similar for whatever tool or language you're using, so it's very important that you get those right from the start. We're then going to switch over to the right side here. We're going to look at the more implementation of these theory in practice. And today we're going to focus on ML.NET, which is the Microsoft's open source alternative to Scikit Learn or any Python libraries. And if you have any time left, we're going to build our own model ourselves in 10 to 15 minutes, just using some simple data samples here, and see how we can construct our own C# program to train our own machine learning model and understand what are some moving pieces and what are not some moving pieces. And if you have any questions, I think there's a Q&A session here as well, so you can drop some questions in that chat, and we can definitely get to them at the end as well. So hope you'll enjoy. So first of all, real quick here, what is machine learning, right? You by now know exactly what machine learning is. If you asked this like 5 years ago, there will be some strange answers probably, and not everyone would really get what it's about. But as this is getting more and more mainstream, maturing, everyone kind of has an idea of what machine learning is right now. It's on your phones all the time. It's on Alexa, Google Home, image classification and face recognition. It's everywhere around us, and even in smaller spaces than you would actually realize, and mostly in recommendation systems on the web or in your apps. All of those things are actually machine learning. When we talk about AI and machine learning and deep learning, though, it's very easy to get lost in the forest here because it's a very flourishing space and flourishing community, and there's a lot of things at work here. But in general, when we talk about machine learning, that's a smaller subset of the bigger umbrella of artificial intelligence. Where artificial intelligence is something that enables computers to mimic human behavior in some sort. And that encompasses a lot more than just machine learning. It's linguistics and other kind of sciences that are related that helps build that human behavior, if you will. If we talk about deep learning, which is very often on the news lately, and talk about neural networks, that is a subset of machine learning. So you get even more specialized and you work on large neural networks and sorts. And I usually think of deep learning as machine learning on steroids. So we take, the classic machine learning algorithms and we just kind of hijack them and just pump in steroids. And suddenly we have deep learning as something that can solve amazing problems for us, but are not always needed. But in essence, machine learning always comes back to one thing for me. It's about programming the unprogrammable. As a software engineer myself here, that's kind of moved into the machine learning space, there are some kind of problems that I just can't solve with regular code because the number of permutations I need to go after is just enormous, and I can't. It's no point of making so many if statements and else statements, and I just can't program that solution. It needs to be much more journalistic to be able to solve it, and that's where machine learning comes into play. And to give a good example of that, I want you to watch this short little video here to understand what we're talking about.
Is this a deception? Do you intend to destroy yourselves?
Just to show you how primitive humans are, Tulosian.
We had not believed this possible. The customs and history of your race show a unique hatred of captivity. Even when it's pleasant.
So who are they, right? Well, I think you recognize them. It was Jeff Bezos, Amazon's owner and founder, and we had Elon Musk as well on the other character. And obviously they did not record this episode back in the day, but this is something called deep fakes, where you superimpose someone's not only face, but expressions and everything about your facial characteristics when you speak and everything else to make it super, super real. And it's not like they've ever spoken these terms and you can just kind of cut and paste them in there and put them above. This is the real actors underneath here actually talking and speaking, and we're just mimicking the facial expressions and the face of these two famous people and putting it into this movie right here. And it's a really evolving field here in deep learning that's really cool and also really scary. But of course, this is something you can never, ever just program in a program because there's just so many permutations here that you need to take into account. So when we build a machine learning model, though, on the right here, how do we get that? And what is a model really? And what is all these terms? Well, the end goal of any kind of machine learning endeavor is ending up with a model that we can use to predict unforeseen data or unforeseen circumstances. And to get to that point, we have to go through a process called training, where we just pump in loads and loads of data of varying sizes into this algorithm that we choose. And the algorithm just kind of iterates over this data until it fits its internal parameters and coefficients and weights and biases and so forth to the specific data set. And that will allow us to then use unseen and untrained data on this same thing here to get predictions that we can trust and that we can see. So if you dive into the model itself or the training process, what is it really and what are some things you should think about? Well, first of all, it's at the bottom of the things, it's linear algebra and it's a lot of math, but we don't need to worry too much about these intrinsic things really. We just need to know we're trying to predict something based on some input data. And there's two terms here that I think is important to learn when you get started with machine learning, and that is features and that's a label. Features is going to be your data columns in your data set, and the label is going to be what you're trying to predict. So we take a very simple example just to kind of highlight these differences. Let's say you want to predict house prices in a neighborhood, and you want to see, okay, 5 years out, what is my house going to be worth? Well, the features here are things that actually make sense to predict house prices, like square footage, number of bedrooms, number of bathrooms, your location, zip code, all those things. They actually have statistical value and will help predict your outcome. And Y, which is a label here, it's going to be the price prediction, and so the actual amount that you think you'll get. So those are two very important terms to think of and remember throughout this talk, but also throughout the time you get started with machine learning. So when we talk about machine learning, there are generally a couple of different types of machine learning, and there are many more types than the ones you see on this slide. But these are the most common ones, and I would say the first one is the one you will mostly encounter in organizations today, especially when it comes to organizations starting off machine learning. You usually get more bang for your buck in this sense. So we have supervised learning here, and unsupervised learning, and we have reinforcement learning. So what are the differences here? Well, supervised learning, the idea behind supervised here is that you're going to teach the algorithm in a supervised manner, if you will, which means that you have data with different columns, but you also have the historical data there, so the labels themselves. So for example, predicting prices for houses or stock market or something like that is a supervised learning experiment, because you will train your model based on historical data. Same thing with predicting tomatoes or bananas in pictures. You will have pictures that are labeled with tomato, banana, whatever is in the picture. So the algorithm can then understand what is actually there and then try to create a model that makes sense to predict unforeseen pictures or other things. Unsupervised learning, though, is the case where you don't have the labels. You have no idea what the data really is, you just know it's data. And a good example when you can use this is for clustering. So for example, you may have a client database of your clients of whatever industry you're in, and you, for example, want to create a marketing campaign against a specific subset of the clients. And you've tailored it out and you know it works really well for this client that you have right here. And you're trying to figure out, okay, this worked really well for this client. What other clients can I apply this to? Well, you can use something like clustering or principal component analysis to cluster and aggregate similar clients in a three-dimensional space. And you don't really know, there's no labels to them because you don't know exactly what they are. You just know they are related. And that's what unsupervised learning is all about, finding these relationships in your data. And same thing, you can also use this for anomaly detection. So you can understand if you have a positive trend in some kind of signal, or if you're spiked, or those things that are super useful for industrial systems or other kind of IoT devices. Reinforcement learning is kind of a hot topic right now. It's all about rewards and penalties. Usually used a lot in like game development, but also you'll see it much more for robotics right now and for understanding how they will see the environment around you. And it's all about really kind of having that use case where you don't necessarily have a direct feedback mechanism. Like for example, let's say you have a bike that is balancing on two wheels, right? You don't always know exactly which decision of that balancing machinery, whatever you have, that is actually causing it to balance and get out of balance. It may be something that happened 10 steps ahead of time here. So you can use rewards and penalties to have like a longer feedback cycle, but still get the same kind of learning experience. All right, so that's machine learning in general. And now we're going to tune up a bit, and we're going to dive into the world of deep learning to understand what deep learning is all about and what we can do here as well. And I will preface this by saying you shouldn't be scared of deep learning. Deep learning sounds scary, and it definitely can, in many ways, be very complicated. But actually, under the surface, is pretty straightforward once you understand some of the basic concepts here. And I'm going to hope that I can explain that in some kind of way that you will at least come out of this talk interested and want to learn more about it. So deep learning goes hand in hand in neural networks in many ways. And neural networks is kind of something you see on this picture right here, where we have multiple neurons, the green dots, kind of set up in some kind of structure from left to right. And this is something called a fast feed-forward network, where you have inputs and you have outputs, and in between you have hidden layers. And if you have more than 2 hidden layers, and in this case you have 2 hidden layers, it's called a deep neural network, or a DNN. And all of these neurons are connected with each other in one way or another. And this is of course only abstract, but they're still connected in some ways. And the signal for one neuron feeds forward to the next neuron and the next neuron and the next neural network. And in each neuron, one calculation is occurring. Okay, a lot of math there. But let's give a better example instead. Let's think we want to do fraud classification. So we're trying to predict fraudulent transactions in a bank transaction, for example, for your credit card or something else. So at the end here to the right, the output is going to be, is this transaction fraudulent or not? So it's a binary choice. It's a binary classification example. So either it's fraudulent or it's not fraudulent. On the left side here, we're trying to then input data that we think will in some way affect the outcome. So let's say we decide that the type of transaction is important. Is it a debit or credit card, or is it a, I don't know, transfer of some sort? The amount transferring, if it's a small amount or large amount, and probably most importantly, the location relative to where you currently are. So if you are in the US and something is happening in the UK, it's probably not a good idea, and so forth. So we can input that data into our neural network, and then the network itself is going to kind of disseminate that data for you in the hidden layers and try to figure out the relationships between those in such a way that it can map the input to the output. So it's just a kind of complicated way of doing a mapping of data structures, but in a multidimensional space, because each of these inputs is another dimension to your network. And sometimes you can have thousands of these inputs. So it scales very quickly, but then it can still handle some of these big loads here. So if you dive into one of the neurons in particular here and look at what's going on in one of these neurons, you'll see that we have inputs here from other neurons to this neuron. And the math that's happening inside this neuron is actually pretty simple. All we're doing here is we're taking the input from other neurons, so x1, x2, xn, and we're multiplying that with a weight that is random. It's a random value, probably between 0 and 1. And we're adding all those inputs together here to get our y. And that's what we're sending to the next neuron in the chain. And yes, of course, we're doing some normalizations in between. We're doing some other small stuff here, but in general, that's what we're doing. We're multiplying our inputs with a weight, summing them all up, and then sending them off to the next neuron. Sounds simple, right? So how does the network actually learn? How does it adjust? Okay. Well, let's look at some of the building blocks in a deep neural network here and understanding what they do and how they kind of fit together. Well, we already saw the neuron. That is an extraction of linear algebra. So we have some math going on in there, right? And an epoch is more or less a term that is commonly used for sending all of your training data through a network one time. So if you pass it through a network one time, it's one epoch. You usually want to do multiple epochs because during each epoch, the network will learn something, and you need to pass it again for the network to learn some more stuff. But the key here that I want to put your attention to is the word backpropagation. Backpropagation is the way that the network actually learns, because you have that, the addition and the multiplication in the neuron that's occurring, but without a learning mechanism, that's going to be the same thing over and over again, and it's actually not going to get any better at distinguishing data and understanding how predictions work. But the backpropagation, what happens here is that at the end of the network, when we actually got to the end of it, we'll actually get the result. So for example, we'll say, yep, this is a fraudulent transaction, but maybe it actually wasn't a fraudulent transaction. So we can use something called a loss function to calculate how far off the network were. More or less saying you were really, really off this time, or you were pretty close. And based on that loss function calculation, we can use something called backpropagation to feed back into the network and adjust the weights in each step of the network. So, we had a random weight here in the beginning, right? Maybe that was 0.5 one time. and we were really, really far off in our prediction. So we're going to go back through the network and adjust those weights, maybe to 0.8 this time or 0.9. So the next time we feed through data during training, we may either be closer or we may be further away, but the network can then adjust itself to get to a point that is a global minimum in this case. All right, I hope you're still with me. We've gone about 20 minutes in this talk, and this is definitely the most heavy theory session of the talk, but I do really like to talk about it because it's important to understand that. I know it can sound complicated, but just think about the simplicity within one of those neurons and what it's doing. But a good thing is we don't necessarily need to know all of that math and all those details when we work with MLNET, but it's kind of fun sometimes to understand how it works underneath the hood. But now we're going to go and look at the machine learning lifecycle instead and understand what steps we need to take to get a model from the data stage all the way to production. And in general, when we do this, we talk about these 6 steps here, which is gathering your data, splitting your data, transforming it to some way that the algorithms can understand, training a model, evaluating the performance, and then putting that in production. So what are these steps more in detail? Well, the first one is also the most important one, I think, which is gathering your data. And it may sound very trivial that you just want to get your data in order here, but you need to think about how the data is structured. So you want a lot of data, first of all. A model can't be trained on a small amount of data. You need thousands of rows at least, and probably more. You also need wide data, so you need a lot of columns for your data. If you can think of any possible parameter that can help in determining outcome, you should probably include in your data as well. And you also want to look at both private data within your company organization and couple that together with public data that may be available for you. There's tons of available data in AWS, in other places as well, that you can use to shape your data for your predictions here. But once you have your data, you want to split your data into a training set and a test set. And the training set is going to be kept on the side here, or sorry, the test set is going to be kept on the side for later to evaluate the model's performance, while the training set's going to be the set we train our model on, of course. Usually this is like an 80 to 20% split, so you keep most of your data to train your model on, and the rest you use for evaluating the performance. Before you can get started though, you need to transform your data set first. There's a lot of limitations on what kind of data an algorithm can use to train a model on. For example, you can't have any strings in your data set. So any text that you have that needs to be transformed in some ways to a numerical representation. And there's tons of good built-in versions of this and options, but just be aware that things like a car make or a person's name, if you use that, or the country they're from, those kind of things, they need to be transformed in one way or another to string. You also need to remove any missing values or null values in there and outliers, things that can really set your model up to just going down the wrong rabbit hole, honestly. Because remember that you want to train the model on what is a normal kind of setting, if you will. So you need to make sure your data is cleaned in any way possible before you train your model on it. So once it's transformed and cleaned up, you want to train your model. And you want to train your model on an algorithm or on many algorithms that you choose. A lot of people usually think this is the most complicated step because you have to pick an algorithm. And the algorithms all sound very scary and they sound very math focused, right? We're talking about support vector machines. We're talking about logistic regression. We're talking about all kinds of things, honestly. There's so many ones here. But what I always recommend here is that you should try multiple algorithms. Just try them. It's cheap, it's free. Just train it again and see what happens. And then you evaluate how good your model actually performs. And then you decide which one you want to go with after that. The more experience you get as a data scientist doesn't mean you will pick the right algorithm directly. It just means that you have a hunch which one is going to be better than the others. But you still want to try a lot of the algorithms anyway, just to see if you had the right one or not. So just be brave here, try a couple of them. Also read up on documentation. There's good Microsoft Docs on this topic, so you will get a good feeling from the start which one is working for you here as well. So once you have trained your model, you want to evaluate your model. So you want to see how good it is and really how it performs in the wild here. And this is why we save the test data set, because there's a real chance here we have something called overfitting, where we train our model on our training data, so it memorizes that data. It's just super, super good at that data. Perfect fit, and that's fine. The issue with that is that if you overfit your data, it's going to be really good at data, but it's going to be really bad at everything else that it will throw at it. So real data from the wild here is going to say, I have no idea, I only know this, but I don't know that. And you want it to generalize well, because that's the whole point of it. If we do exactly all the parameters, we just do normal programming skills anyway and just write if statements, and we have a rule engine, and that's all good. But we don't want that rule engine that's so stiff, and that's usually overfitting. We want it to be slightly loosely coupled there. So we don't want to overfit, we don't want to underfit, we just want it to fit nicely snug around our data points. So when it actually gets new data that it doesn't fit completely into the mold, it can still give a pretty good prediction of that data to understand what's going on. And usually at this step here, you look at metrics such as accuracy and F1 score and all kinds of stuff here. And they have, again, pretty complicated names, most of them, apart from accuracy, I think. But there's some really good documentation to read up on what they mean. In general, you always kind of start with accuracy, I think. But you need to be aware of the fact that most of the time, you also want to look at things like F1 score and recall and precision and other stuff like that to really understand how good your model is. Because accuracy can lie to you, and it can lie pretty badly. And you may think you have a really, really good model, but actually it's very biased in many ways or not just. And that's going to hurt you as you go forward. So once you have evaluated your model, you come to the last step here, which is deploying it into the wild and letting it out. And if we talk about MLNET, this is really where MLNET shines, because you can deploy it wherever you want to, really. You can put it in an ASP.NET Core application, Azure function. You can put it on your local desktop app or even on a mobile device. It really depends on where you want to serve your models. And it depends on the use case. Sometimes you want to do it in the cloud, but sometimes you want to do it on the edge as well. So you have to think about that. But there's tons of use cases for this. Docker containers or embedded into your app. It depends on what you want to achieve. All right. So before we get started, we're actually coding here, which I want to get to. Let's kind of dive into what MLNET is, though. So MLNET is a machine learning library for .NET developers, and it was kind of released about 2 years ago at MS Build, but it's been been around for a long time before that. It's open source. You can go to their repo and submit issues or PRs, or just in general check it out. It's cross-platform, so it's great because you can run it on a Linux container in Docker, and of course it runs on .NET Core, so we'll get all those nice performance boosts that .NET Core has as well. Again, you can deploy it wherever you want to. An Azure function is a good one, but containers as well. And a really cool feature of the library is that you have something called the model builder, which is more or less an AutoML feature. So if you are getting started with this, you don't actually need to write any code. You can just pass it the data and tell it what to do, and it will spit out a model for you that is reasonably good, and also tell you how it actually created the model, because it will also give you the code samples for the specific use case. And the model builder is good because you can use it through Visual Studio and through the CLI, as well as through an API. So depending on what works for you. If you worked with data science a bit before, or you kind of been in the sphere in the community, you may have heard of Jupyter Notebooks as well. And Jupyter Notebooks is a really cool tool, really, to both work with machine learning training, but also visualizations of your data in a notebook of your choosing. And until November of last year, you couldn't really do that in C#, but they now released the .NET kernel that allows you to run C# into Jupyter Notebook as well. So you can do kind of graphs on your data and see everything live. And it's a really, really nice addition. I like it a lot. It's a very good way to get started with machine learning in .NET as well. Finally here, there is support for deep learning in .NET, in ML.NET. It's not as great as you would have in other libraries, but under the surface, they use TensorFlow, which is Google's deep learning flagship. And you can either train your own neural network using ML.NET with TensorFlow bindings, or what you can do is something called ONNX models. So it's Open Neural Network Exchange, which is an open deep learning standard between Microsoft and Apple and Google. So what that means is that you can train a model in ML.NET and export it to ONNX, and then they can use it in whatever they want, in Python, in R. Or what you can do, which is more powerful, you can take an existing deep learning model in Python, and you can export that to ONNX, and you can actually import it into your .NET applications. And that allows you to really take off the shelves deep learning networks here for object detection, for example, and pipe them into your ASP.NET Core applications. So you can actually do deep learning live without training anything at all, but just using the model, which is really cool. So definitely check out ONNX. I think that's one of the strong suits of the library and the ecosystem in general. I like it a lot. So we will see this flow in just a bit, but in general, what happens here when we build the model is that we have our data into an in-memory dataset called an iData view. And what we do with that dataset is that we will create a data pipeline on it to transform our data. So remove missing values and null values and so forth until we finally have a pipeline we're happy with. And at that point, we'll pass in the algorithm and train a model and then evaluate the performance. And this thing can kind of iterate multiple times until we're happy with it. And in that case, we save it to disk, and that's going to be a zip file. And that zip file can then be loaded into memory somewhere else. And we can then use that zip file for predictions. And we'll see what that is all about in just a second. So if you want to get started off this talk, what I will encourage you all to do is I will go to the community samples that are on this ML.NET repo, the first link here, which more or less have an example of every kind of model that we need to train in ML.NET. And that's a really good way to get started and understand what you can do and what you can't do in ML.NET. I also created myself some .NET new templates for ML.NET, and we'll use them in just a bit here, which will allow you to directly create a solution more or less with the general structure of how you want to train a machine learning model. So you don't need to think of all the moving pieces and parts here, but just focus on how your pipeline should look like and what algorithm you want to choose. And again, if you get started with this and you like it and you want to put it in production, check out MLOps.net, which I'm currently building with some other people around the world. That's going to support the whole deployment experience to deploy machine learning models production, to make sure we have an audit trail on the data used and the algorithms and everything else, which is going to make it much more of a seamless experience that we're used to in the development community. All right, so 33 minutes of talking, which is good, which leaves us with enough time, I think, to build our own model. So let's do that. So what are we going to do today here with the last few 10-15 minutes of this talk here? What I want to do is I want to build a machine learning model to predict if you survived the Titanic or not. So the Titanic, of course, we're all kind of aware what happened there, but a lot of people died and some people survived here. And this here is a data set of those people, more or less, where we have people like James Moran here, and we have Eugene Rice, and we have Anna McOwen. And we can find data about each of these passengers here, about their gender, about their age, about their siblings and how many siblings and spouses they had aboard, and which passenger class they were in, so P class. Maybe they're in the third class, in the first class, and the second class. And most importantly, if they survived. So we see here 1 is that they survived, and 0 is they did not survive. And already now, we know that this is the label. This is a supervised machine learning model we're going to build. that is a binary classificator, because it's only 2 choices. And all of these other columns here are your features. So those are things that are going to be useful to make a prediction or not. Hopefully that sounds good so far. So how are we going to build this model? Well, let's use our templates that we already have available to save some time here. So there's a NuGet package available for you if you want to. And what you can do is just copy this CLI command right here, and you can install these new templates locally on your machine, which is going to pull down some project templates for you. So if you do that, what we get here are a couple of new ones here. So we have these MLNET console app for training. We have an ASP.NET Core web app for deployment and so forth. And we're still adding new ones here, but in general, this is kind of the templates you get here. What is cool with this is that we can do something like .NET new, which is the general command for .NET, and we can say MLNET training, and hit enter. And what it's going to do is create a project for me with a simple thing here. And we can then, I think what we can do is actually go ahead and let's see, sometimes it doesn't want to do this or not, but let's open up Visual Studio Code here for us. All right, take this away, zoom in here because I think it's a bit small. All right, perfect. So what I did here is that we have created a simple project here. We have a CS proj, as we always have, and it will pull in the NuGet dependency that we need for the MLNet library, which is called Microsoft.ml. And the current version is 1.5.2 actually, but this is an older one here. Perfect. So what we see here now is we have a schema. So we have a model input that we need to fill out. We have a program file here, which is a console application, and it has a general flow here, very similar to the lifecycle I spoke about before, where we're loading our data, we're splitting it, we're transforming the data, training our model, evaluating performance, and then finally we are saving it to disk. So what this template does for you is it gives you some of this boilerplate code here already started. And primarily what it does here is loading of a text file. So you can see here that we are using something called MLContext. And MLContext is kind of where everything resides on for MLNet. So this is an MLNet construct specifically used for this. And it is structured in a way, I'll remove this for now, that you have catalogs here. So we have a binary classification catalog that we will use a lot, and different types of ML tasks here. And we also have things like model to save the model and load the model. We have data to load our data and so forth. And the way we go about this is the first thing we want to do here is define where our data is. So what we're going to do here, and I think what I'm going to do actually is open Visual Studio instead, because I think it'll be easier for us to see and use here. So let me do that real quick. Open up an instance, because it will allow me to actually I think it's fine. So the data is actually here. So I'll just copy the whole path instead. It's a CSV file, right? And we looked at that just a bit ago here. So we can define the path to the data like this. We can escape some symbols, and there we go. And when we load the data, we can load it from a text file, which is what we're going to do right now. And we're going to define the data path and the fact if it has a header or not, which it has, and what kind of separated character it has. So it's a comma separated file, so a comma here. The default is tab separated. And other things we need to define here is the schema. So we need to have a generic class here to define what the structure looks like. And in our case here, we're going to have two different, we're going to just include a couple of columns here, not all of them, to save some time here. But the first one we're going to do here is the label. So it's going to be survived, right? We'll make that a property. And the second thing we want to do here is something like, maybe we want to do the sex of a person, sorry, the age. So we'll do the age of the person here. And then finally, just to make it a bit interesting, we'll do the gender as well here. So we'll just use 3 columns for now here. But something we have to do here as well is to define the order of them. So we have survive as the first one. So what we're going to do here is use an attribute to define the order. And that's an MLNET attribute. It's called load column. And we'll use the index of 0 here for survive. So it's 0, 1, 2, 3, 4. So this one has number 3. And the other one has 4. Okay, so we'll do load column 3. Low column of 4 here. And that just lets the library know where in the CSV file it will find this data. Oop. And that's kind of all we need to do on a schema like this here. It's all good. Oop, don't save that. I want to save the file as well. Save all. Okay, good. So if we run this right now, it's going to load the data into the iData view. And then the iData view we can then pass into this train test split method here, which is going to split the data into a training and a test set. So it's going to keep about 10% of the data in a test set and the rest in a training set. So what we need to do ourselves here is fill in this data processing pipeline here. And that is to tell the library how we're going to use this data. And there's a couple of things we want to do here, but the first thing we want to do is we want to convert that gender column to numbers, because right now it's a string. So we want to convert it to 2 columns. One is female and one is male. And it's going to either have a 0 or a 1 in it, depending on if it's a male or if it's a female. And we can do something called one-hot encoding to do this. Oracle one-hot encoding. And what that does is just takes the, so let's do like this. It just takes a column and it will, behind the scenes, take that text column and it will transform that to 2 binary columns. So one is female and the other one is male instead. And the second thing we want to do here is we want to replace missing values. So we can append here another method. So append. Let's see, transforms. So we have in the age column here, you may have seen that we have a missing value. So we're missing an age for a person here. And we need to replace that in some way or another. And what I'm going to do is I'm going to replace that with the average age of all people, just to kind of blend it out a bit more. At least it's not going to be an outlier in any means here. So we have this replace missing values transform right here. And what we can do here is just pass in the name of the column. And then we can pass in the replacement mode. And that's going to be, let's see if we get that, mean. Okay. And then finally, what we're going to do is append the final concatenation here. So the final thing we want to do is we want to add these together. So we want to say, okay, please create, let's see, please create a column for us called features, which is the feature vector we'll use to train a model on. And that's going to be based on my my gender column, and it's going to be based on my age column. So what we're doing right here is just telling the library to use both these columns for your prediction, and you concatenate those into features columns that is deciding that for us. Cool. All right. And then finally, what I want to do here before we train this model here on the fit method is do the trainer. So we have to have this data processing pipeline here to pick a trainer that we're going to append to it. And again, this is also an MLContext, and you'll find it under, let's see, the ML task you're doing and the trainer's place. And we're going to use something called logistic regression for the specific use case right here. And in this case here, we just need to pass in the label name, which is survive. And that should be everything we need to do. So you need to know which column we're trying to fit our data to, which is survive in this case. And this rest here is just appending that trainer here to our existing data processing pipeline, and then it's all good. So before we can train this, we're pretty close to training it now. We just want to evaluate the performance here of this model. So in our case here, we need to do two things. We want to take our test data and use the trained model that we got right here to transform that to predictions. And then we want to calculate how good those predictions were. So we can take the trained model here. So as model.transform, and we can take the trained test split here, the test set, to get predictions. And those predictions can then be used to calculate the metrics. And the metrics is going to hold things like the F1 score and the accuracy and other things like that. So the way we do this is by using an evaluation method on the ML task here to do that. And what we're going to do is going to pass in the predictions to this one, and we're going to again pass in the name of the label column here. All right, that should be everything you need. And I'm sorry if I went a little fast here, but I want to make sure I have time to run this. So I may have missed some settings for Visual Studio Code here, but let's go and see, hit F5 here and see if we can get this running. Hopefully. Sometimes I always miss something here and doesn't want to start, but we'll see if it works this time. If not, that's not the whole world. Dun, 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 dun. I think it's building. All right, so hopefully we haven't misspelled anything here. So you can see here, we're loading a text file. We have the data now into a memory representation of that. And we're splitting the data into two sets, test set and train set. We're creating our transformer here, and we're picking a trainer. And this is where it actually takes some time. This is where we're going to train it. So we had an issue here. And let's see if there's something I need to fix real quick, or if we can wait with that. Oh, sorry, I know why. Never have the text file open at the same time you're running an experiment, because it's going to be a process that's locked. Let's try it real quick again. Hit F5, skip this breakpoint, drag it to the side so you can see a bit more. So let it run all the way here. Perfect, a bit better. All right, so we train our model real quick because it's a small example, and the metrics here is visible. So you can see we have an 83% accuracy, which is pretty good, and we have an F1 score of 0.74, which is not too bad. And we want all these values to be close to 1 as possible, mostly. And that the more close to 1 they are, the better. And there are some exceptions, of course. And if we let this go all the way to the end here, we'll eventually save the model as a zip file on disk. We can use that for anything else, for reference, and we're good to go. Awesome. So I know I ran through the last piece pretty fast here. If you want to look at a full example, I got it in my GitHub repo. You're more than welcome to look at it. It's called Titanic MLNET, and you can dive into more examples. But you can also look at a community examples page for more of the examples. But in general, it's once you've done it a few times, it's pretty same thing over and over again, so you will get more accustomed to it. But I just want to thank you all for joining into this talk today, and if you have any questions, I'll be here to answer them for a bit. Over to you, Stan.
Thank you very much for that great talk and awesome demo. It's going to take a couple seconds for people to hear what we were saying, and so we'll give them a couple seconds for questions.
Sounds good. If you have questions afterwards as well, you can find me on Twitter or LinkedIn or whatever medium you prefer, and I'm more than happy to answer them there as well. All right. Well, thank you all for joining in. I had a great time speaking about this topic. As you probably can tell, I'm pretty passionate about this topic, and this is what I do most of my waking amount of time when I don't work in my regular work. So if you have any questions in the community, we are a very happy community, and it's very global. We have people from New Zealand and India and other parts of the world, and we would more than welcome any new people to our community. And we have a virtual Slack room for anyone who wants to kind of just chime in and get started. It's a pretty vibrant Gitter channel. So more than happy to welcome you with open arms if you're curious about this topic.
Thanks a lot, and I will